Okay, so in previous recordings, we looked at the interaction of charged particles. So if you haven't done that yet, go back and look at those recordings. What happens if we have multiple charges interacting? So not just two, but 3 or 4 or 7 or 8. How do multiple charges in the same space or multiple charged objects in the same space influence each other? So this mini lecture is going to look at this idea of superposition and what happens when we have multiple charges interacting. And this mini lecture will look at it from a conceptual standpoint. And a later mini lecture or another mini lecture will look at an example problem from a mathematical standpoint. How do we actually determine the net effect of multiple charges in an area? So multiple charges interacting, and this is of course conceptual. Okay, so let's imagine that we have 3 charges in a space. So we have Q1, and we'll say Q1 is positive. We're going to have Q2. We'll say Q2 is negative. And then we'll have Q3. I'm going to put Q3 over here. And we'll say Q3 is also positive. And the magnitude of Q1, the magnitude of Q2, and the magnitude of Q3 are all going to be the same. So we're going to have the same strength of charge, just different locations relative to each other, and some are positive and some are negative. All right, so what forces does Q1 feel? Let's look at that force first from, again, a conceptual idea. So what net force does Q1 feel? What does that look like? Well, we know that Q1 is interacting with Q2, and we know that Q1 is interacting with Q3. So like you may have learned about forces, and if you haven't, you can go check out those force videos. Like we talk about net forces acting on an object, multiple forces, multiple push and pulls, net electrical forces can also act on an object. And we have to look at the vector sum of those forces to see what the total force is acting on that charged particle. So we have Q1. We're going to take each force independent, just like we can look at the forces, net forces acting on motion independently, and then bring them together. So the force that Q1 feels from Q2, well, Q1 is positive and Q2 is negative. That means they attract. Opposites attract. So if Q1 is attracted to Q2, then it feels a force in that direction towards Q2. So I'm going to represent that force with an arrow of this length. This is the electric force Q1 feels by Q2, and it's to the right. All right, well, that's what Q2 would do, but what about Q3? Well, Q1 and Q3 are both positive. Positive charges, like charges, they repel. So if I look at the force Q1 feels from Q3, it's in that leftward direction. All right, so I'm going to draw that force on Q1 as my vector representation. But I want to be careful. That length of that arrow is going to represent the strength of the force. Now the charges are the same, we said, but Q3 is further away than Q2. Maybe 3 times further away. 1, 2, 3. Sure, 3 times further away. And when we think about Coulomb's law, the radius plays a big role, right? As we increase the radius, we decrease the force by a lot, the square of the amount. So if it's 3 times further, the force is 9 times less. So the force is to the left, but it's only a portion of the force, the electric force on 1 by 3 is much smaller than the electric force on 1 by 2 because it's so far away. Now I have these 2 forces. There's no other charges that are interacting with Q1, and I can look at the net force acting on Q1 by both charges Q2 and Q3, and the force net is going to be the sum of those forces in the rightward direction. All right, so we look at each force independently, and then we can sum them like we do our forces. Well, let's just do one more. What about Q2? And then we'll look at what happens when those forces are not in a single line. Let's look at Q2 just as a second example. All right, well, the force of Q1 and Q2 is a negative based on Coulomb, which tells us it's attractive. A negative attractive force for Q2 is in that direction towards Q1. So here is our force, and it's roughly the same size. I tried to make it the same size as the force Q1 experienced by 2, Newton's third law of pair. This is the electric force Q2 is feeling by Q1. What about Q3? Well, Q2 is negative, Q3 is positive. That's going to end up with a negative force based on Coulomb, so that's attractive. And in this case, that means it's in that direction for Q2. Attractive force is in that direction. And so how big is that force? Well, the difference between Q1 and Q2's radius and Q2 and Q3's radius, that's about twice the difference, twice the distance. And so again, the radius is proportional to the radius squared, inversely proportional to the radius squared. So it's about a fourth of the strength of that force, and that direction. So we have the force in that direction on 2 by 3. And then we can, of course, look at the net force acting on Q2, and it's going to be to the left, would be our net force on Q2. So just like we sum forces vectorially in our forces in motion in situations, they're just forces. They're all going to be added vectorially. And so we can do this idea of superposition to add our forces, our net force on our objects. All right, well, that's pretty straightforward. They were in a straight line, but what if they weren't in a straight line? Well, it's just like we added forces vectorially in motion. No difference. I'll say it again. We just have to consider their angles. So let's do a quick conceptual example of that. Imagine, I'll use our same 3 forces. So we have Q1. Let's say Q1 is here, and again, it's positive. Let's put Q2 up here, and that'll be negative. And then we'll put Q3 here, and that one again is positive. So now we have them in 2 different dimensions. Well, let's look at the net force on Q1, and we'll just do the force on Q1. Again, we can separate each force independently and then smash them together vectorially. So Q1 and Q2, if I calculated the electrical force on Coulomb's, based on Coulomb's law for Q1 and Q2, I'd get a negative force. Negative force means it's attractive. Opposites attract. And so Q1, attraction for Q1 is an upward force from Q2. So that's the force on Q1 by Q2. What about Q3? Well, those are both positives. Likes repel. So those forces are going to be repulsion. For Q1, repulsion means to the left. So the force, the electric force on 1 by 3 is leftward. So what is our net force acting on Q1? Well, we can do this graphically, our vector addition graphically. I take my electric force by 3 on 1, kind of shift it up there, and then I can draw the resultant force. So this is the net force on Q1. All right, so those vector components, back to that trigonometry when we added those 2 forces. So Q1 feels an upward force, but also a leftward force. And so up and to the left is our net force acting on Q1. All right, so same ideas we did with forces. We can look at each of the forces acting on the object individually. We can break those components apart. We'll do that in an example problem mathematically on combining forces acting on multiple charges conceptually. And we can just imagine each force acting differently and then adding our vectors. Good job.